All right, continuing with our circles, finding arc measures, section 10.2. Our objectives: to find arc measures, identify congruent arcs, and prove circles are similar. And then our essential question: how are circular arcs measured? Once again, we have some vocabulary we need to make sure we are aware of. We have central angles. Those are the angles whose vertex is the center of the circle. So here we have an example, angle ACB, and the angle's vertex is right there at the center. That's what makes it a central angle. Then we have minor arcs. So if the measure of angle ACB, our central angle, is less than 180 degrees, then the point on circle C that lie within the interior of angle ACB form a minor arc. Our example is this part of the circle that's highlighted in red, which we use our symbol, arc symbols, are like little curves above our two letters. The two letters are the end points of the arc. Our major arc are the points that do not lie on the minor arc. So in other words, when our central angle is greater than 180 degrees, we're looking at a major arc. Example, arc ADB. So follow the letters in order. A is an end point of the arc. Go all the way around, including D, towards B, the other end point. So you have to have the end points named, and then any letter on the circle to be the third in the middle letter. Then your semicircle are arcs with endpoints that are the endpoints of a diameter. And that means it's exactly 180 degrees. All right, so when you measure arcs, it's always in degrees. The entire circle, as we know, so that's all the way around the circumference, 360 degrees. Our minor arcs are always equal to the measure of the central angle, and our major arcs are always equal to the difference between 360 degrees and the related minor arc. So in other words, 360 minus your central angle. All right, so let's practice finding the measure of arcs. Let's find the measure of arc RS. So that's from R to S. And its central angle that intercepts this arc is 110 degrees. Since arc RS is a minor arc, then the measure of arc RS is equal to the measure of angle RPS, which is 110 degrees. Next, we have our major arc TS, major arc R to T to S. It's the other part of the circle, so we would subtract from 110 degrees. And it is a major arc, resulting in 250 degrees. And then we have the measure of arc RST, which looks like that is a semicircle. So from R to S to T. So if it's a half a circle, that's 180 degrees. All right, so the next vocabulary we have is adjacent arcs. Well, just like we had adjacent angles, those are angles that are next to each other, sharing the same vertex point. We have adjacent arcs, and that's when two arcs of the same circle have a common endpoint. Example, we have arc AB, and it is sharing an endpoint with BD right here at point B. So our postulate, an arc addition postulate, states that the measure of an arc formed by two adjacent arcs is the sum of the measures of the two arcs. So if we add those two adjacent arcs together, we will get the sum of the entire major arc from A, including B, towards, actually that should be a D right there, not a C. So the measure of arc ABD would be equal to the measure of arc AB plus BD. So just fix that on your implied statement list. All right, go ahead and take a moment, pause the video, and you try the arc addition postulate with these three examples. All right, did you get these answers? 120 degrees, 230 degrees, and 130 degrees. If not, take a moment to look over the explanations here to see if you can identify your mistakes. If not, bring in clarifying questions to class. This next one is also using the angle addition postulate, but it's in the context of our circle graphs. And we're familiar with these. But in this situation, we have a recent survey that asked teenagers whether they would rather meet a famous musician, athlete, actor, inventor, or other person. So this circle graph shows the results, so find the indicated arc measures. So take a moment to pause and try these on your own and see how you do. All right, there's your answers. See how the results ended up. And if you made any mistakes, maybe take a moment to identify where you might have identified an incorrect value, or maybe added instead of subtracted, or subtracted instead of added. So check it out. All right, next we have our next two theorems and some more definitions. So let's take a look at the next theorem, congruent circles theorem. It states that two circles are congruent if and only if they have the same radius. So in other words, if we have congruent circles, this implies equal radii. And here we have an example with a statement underneath that supports what we see in the picture. Plus we have our equal radii, congruent circles. And if you have congruent arcs, there are two things that are always true. You have the same radius, and you must be in the same circle or congruent circles. So knowing that information about congruent arcs, let's take a look at our next theorem, which is about congruent central angles. In the same circle or in congruent circles, two minor arcs are congruent if and only if their corresponding central angles are congruent. Implied in circles, in circle, two minor arcs congruent implies corresponding central angles congruent. So let's take a look at our picture here as a general idea of this theorem. So here we have two of the same angle marks for our central angles CAB and DAE, which means the measure of arc CB is congruent to the measure of arc DE. That's also true the other way around, actually. So what this theorem is saying is that if the measure of the arcs are congruent, then we can conclude that the central angles are congruent. All right, for identifying congruent arcs, let's tell whether these red arcs are congruent, explain why or why not. So in our first example, is arc CD congruent to arc EF, and explain? Well, we can see that the two central angles are congruent. And we know that the arc measure of the angle's central angle that it intercepts is congruent to, or has the same measure. So if both these central angles of the same circle are congruent, then the arcs must be congruent. So yes. All right, our second example, we have arc TU congruent to arc RS. Well, we don't have the same circle, although they have the same center, and these two arcs are sharing the same central angle, which is 90 degrees. But since they are not the same circle, not congruent circles, then we do not have congruent arcs. And then our last example is arc MN congruent to arc PQ. Again, equal central angles, but our radii are not the same, therefore our circles are not congruent, therefore our arc measures are not congruent either. All right, next let's take a look at our proving circles similar. So our last theorem for this section would be our similar circles theorem, and it states simply that all circles are similar. So all circles implies similar circles. So let's take a look at this proof, and I'm actually changing this proof from the one that I had in your notes. So disregard the one that's in your notes and take a moment, pause the video to write out this new given with this new proof and the new picture. All you need to do is just go to your notebook page across from the typed page so that you can write out this proof. So pause the video here. And you can write the new proof on page 37. All right, always start your proof. We're going to do a 2-column proof this time. Start your proof by getting those givens in place and go ahead and start setting up your columns with statements and reasons at the top. And we'll start with the given that OA and OB are radii. And since they are both radii, we know that they are congruent. So we can mark that on our picture. We have congruent radii. So our next statement will be that segment OA is congruent to segment OB, and that's because all radii are congruent. Next, we can move to proving showing in our proof that OP is congruent to itself, and that's by the reflexive property. So as you can see, based on some of the information we already know from this current unit, we've got 2 triangles. So we're trying to prove these triangles congruent. We're given that PA and PB are tangent to circle O. We're going to use that information because we can then conclude that OA is perpendicular to PA. That's by one of our new theorems. Tangent to a circle implies line perpendicular to radius. So we're going to go ahead and add in our right angle symbols. We've got 2 right triangles. Well, if we have 2 right triangles, then that means angle PAO and PBO are right angles. And we can say that because perpendicular lines implies right angles from early in the year, Unit 1. And if we have right angles, that means we have congruent angles also in Unit 1. So we can say that angle PAO is congruent to angle PBO. Reason, right angles imply congruent angles. And since we have 2 right triangles with congruent right angles and a hypotenuse and a leg, we can prove and show that triangle AOP is congruent to triangle BOP because hypotenuse leg of a right triangle implies congruent triangles. And that means all remaining parts are congruent. So angle AOP is congruent to angle BOP by CPCTC. And then let's just finalize our lesson with similar arcs. So 2 arcs are similar if and only if they have the same measure. So we can say that all congruent arcs are similar, but not all similar arcs are congruent. So which of these choices A, B, and C support this second statement? You got it. It's choice B. Choice B is our counterexample that allows us to say that the measure of arc RS is equal to the measure of arc TU, but arc RS is not congruent to arc TU because they are arcs of circles that are not congruent. And I leave you with a bear that also appreciates a solid circle hula hoop. See you in class.